Rogue planets are one of the great mysteries left in the universe. They are planetary-sized objects that are not gravitationally bound to a star. We don't fully understand how they formed. Perhaps they formed in a planetary system but got ejected during the system's turbulent beginnings. Following that thought, perhaps our own solar system also had additional planets at the beginning before they were cast away to forever roam the galaxy alone. Rogue planets could also be protostars that simply failed to absorb the mass needed to become a star or even a brown dwarf. We expect there to be billions to trillions of them out there in just our galaxy alone. Although, because they are hard to detect, this really is an educated guess at best. However, since the turn of the century, we have started to detect a few of these mysterious objects. How can that be when there are no stars lighting them up, and since they don't emit their own light? If they are pitch black, how do we have any hope of detecting them at all? Well, this is where a very interesting detection technique comes in, called gravitational microlensing. On this channel we have explored various exoplanet hunting techniques in the past, mainly the radial velocity method and the transit method. The radial velocity method measures the wobble of a star caused by the gravity of orbiting exoplanets. The transit method measures the brightness of a star over a long period of time that looks for dips in the star's brightness when an exoplanet passes in front of it. However, these methods are only useful for detecting exoplanets around stars, and generally these exoplanets tend to be large and have very close orbits. The gravitational microlensing method is an exciting method because not only can it find exoplanets much further away from their host stars, but these planets can also be as small as Mars, or possibly even smaller than that, and still be detected. Additionally, rogue planets with no star at all can be detected with this method. Sounds almost too good to be true, but there is one catch. So how does it work? Gravitational lensing is a well-known phenomenon in astronomy and has been used for years to detect some of the most distant galaxies that we know of. Einstein predicted this phenomenon back in 1936, and with the development of telescope technology, it has been confirmed by observation. Basically, the further away a light source is from us, the dimmer it becomes thanks to the inverse square law. The reason objects get dimmer with distance is that photons spread out as they travel, meaning the further away you are from the object, the fewer photons that reach your eyes. However, when there is a body with a large amount of mass, like a galaxy or galaxy cluster, the mass of the object warps the curvature of space-time depending on how massive it is. Light follows the curvature of space-time, meaning that if light emitted by a distant object travels past a massive object, the light photons that would have otherwise gone off in these directions bend back around thanks to the object's gravity, making the background object appear brighter to an observer here than it otherwise would have done, as more light photons are reaching them now. Gravitational lensing is very obvious when we look at the biggest types of objects, galaxy clusters, because these objects warp space-time the most. This means that if we are aligned just right with a galaxy cluster and a distant galaxy, the distant galaxy would appear much brighter. The light from the distant galaxy bending around the nearer galaxy would also actually make the galaxy appear stretched, sometimes into the form of a ring. You may have seen these Hubble images before, where distant galaxies appear totally distorted thanks to this gravitational lensing effect. And here is a CGI example of what you are seeing, which may help you understand why this happens. Now, as I mentioned, more recently the use of gravitational lensing has also been used to help astronomers detect exoplanets. Stars and planets are much less massive than galaxy clusters, but gravitational lensing still happens to a small degree. When a star transits in front of a distant star, the distant star will become brighter as its light follows the curvature in space-time around the foreground star. Additionally, should the foreground star have an exoplanet or exoplanets, The distant star will also get slightly brighter when these transit in front of the distant star too. This is the process of gravitational microlensing. This process is so accurate that small Earth or Mars-sized exoplanets can be detected, and potentially even large exomoons. Astronomers simply need to measure the little peaks in brightness to distinguish between the individual bodies orbiting the foreground star. Now, as I mentioned, there is a catch with this method, and that is that star transits are actually quite rare, because they really need to be aligned just right from our perspective, and the galaxy is simply huge. There's so much space in between stars. This is why, up until now, the transit method has had a far better success rate at detecting exoplanets, because exoplanets orbit and transit their stars a lot quicker than stars transit other stars. So, in order to spot these events, what we need is to observe a huge swath of sky in one go. Enter the Nancy Grace Roman Space Telescope, previously known as the W1st Observatory. This telescope, due to be launched in 2025, is comparable in size and will provide images with a sharpness similar to the Hubble Space Telescope, except the Roman Space Telescope will be equipped with a 288 megapixel camera and a 0.28 square degree field of view, which is 100 times larger than Hubble. With this field of view, it will be able to keep track of a much larger section of the sky and monitor for microlensing events. How does this all fit in with rogue planets? Well, much like stars, rogue planets that transit in front of a distant star will also make that star slightly brighter. And if the Roman Space Telescope is looking at that section of the sky, it should be able to detect it. In fact, throughout its 5-year initial mission, scientists hope that the Roman Space Telescope can give us a much better indication of how many rogue planets and Earth-sized exoplanets there are out there. Now, while it is possible that rogue planets are in any section of the sky, the Roman Space Telescope will focus its time looking towards the center of our galaxy. There are a lot more stars here, so transit should be more frequent, and this will increase the chances of spotting microlensing events. It is amazing to me that there are ways to detect these otherwise invisible objects that emit no light, and all you need to do is look at the brightness of a background star, and as a rogue planet passes in front of it, the gravitational microlensing event will reveal key details about the rogue planet, like its mass. So, have we detected any rogue planets this way at all? As it happens, yes we have. There are a few ground-based programs on the hunt for rogue planets operating right now, like Ogle, Moa, and Supermacho. At present, they have found 22 rogue planet candidates in all, with the most exciting one being Ogle 2012 BLG 1323. If this rogue planet gets confirmed, it will be the smallest rogue planet discovered by some ways, being roughly the mass of Earth. How a body like this comes to be free floating in space, we don't really know yet. We're still really early in this field of discovery. But as the James Webb Space Telescope and the Roman Space Telescope launch, hopefully we'll uncover much more information about these fascinating objects. So there we have it, how we can detect the invisible objects that are rogue planets. Thanks for watching, and as always, a big thanks to my patrons and members who helped pick this topic. The poll this time was incredibly tight. I think there was only one vote in it at the end. If you want to also help pick future Astrum Answer episodes and support the channel, consider becoming a patron or a member today. A Christmas treat for me would also be if you could like and share the video if you found value in it. It really helps the channel to reach new audiences and allows me to do more videos like these in the future. So, all the best, and see you next time.